Hello everyone, how are you? Hope you will be fine there. Today we are talking about very important topic, bridging worlds, analog, digital, and back again. Our main topic is converting analog signal into digital signal, and digital signal into analog signal. So we will start. So our topic is bridging worlds, analog to digital, and back again. The invisible translator that connect our physical reality with the digital universe. First we will see what is the analog signal. The physical world we live in, like sound, temperature, whatever that are analog signal. Our senses perceive a continuous flow of information, the gentle curve of a sound wave, the supple of shift in light intensity, the gradual change in temperature. This is the analog world, infinitely variable and rich in detail. In the analog domain, value can take on any point within a continuous edge. A sound wave's amplitude changes smoothly, never jumping between discrete steps. Temperature varies gradually throughout the day. Light intensity shifts imperceptibly as clouds pass overhead. This continuous nature is what makes our physical world so rich and nuanced. So analog signal is what that like I am calling someone, like I am calling my friend. So my voice is a analog signal, but he receive also voice. So but what can a digital device, this phone, what is here? So phone is converting my analog signal into digital signal. Analog signal has a multiple inputs infinitely, but digital signal is only understand zeros and ones language. So uh, ADC means analog to digital converter converts my analog signal into digital signal, and then after that my friend that hearing me in that form, the digital signal convert and in analog form. We will see that again. The world of computers, that is digital, the digital reality. Computers and digital devices operate on discrete values, ones and zeros. They can only represent a finite number of states. Unlike the uncontinuous analog world, digital systems work with the specific distinct values. A voltage is either high or low. A bit is either 1 or 0. A number is one of a finite set of possibilities. The challenge. What is the challenge? How do we translate the infinite into the finite? Means how we translate analog signal into digital signal. How can we capture the richness of continuous phenomena using only discrete values? This is where ADCs and DAC become essential. They serve as the bridge between these two fundamentally different worlds. So digital signal is what the computer, phone, they are only know the knows the zeros and ones language. Only two discrete values, which is zeros and ones. But in analog signal, we have many infinitely inputs. So these are the waveform of analog digital signal. So in analog signal, the waveform is continuous. But in the digital signal, you can see that the waveform is uncontinuous, non-continuous. You can say the voltage versus times graph is a here in analog signal it is a continuous, but in digital signal you can see that it is a non-continuous. We will see that. So the main topic is started from here. The translator, analog to digital conversion. Analogy. Imagine trying to describe a smooth flowing river to someone who only understands counting pebbles. So the first step is sampling, taking snapshots of the analog signal at a regular intervals like frames in a film. Second one is quantization, assigning a discrete value digital value to each sample representing its amplitude. And the third one, the resolution is the number of bits used determines the details. Higher resolution means more precision. Example like a 12-bit ADC has 4096 possible values. An ADC takes a continuous analog signal like voltage from a sensor and converts it into a series of discrete digital numbers. The quality of this conversion depends on the sampling rate, how frequently we take measurement, and the resolution, how precisely we can represent each measurement. What is sampling? Like in upper graph, we can see that they here as analog signal. They're like here at every point there is some point. We are considering the highest point. This is the voltage. At this point, we see the voltage like it is a 250. That nearest point appearing in the topmost point, like it is a 250. That is the quantization. But there is some error. The error call can be called as a aliasing. That is a effect, aliasing effect. There is our analog signal to digital converting. There is a can be error that called is the aliasing. But we need to know that how many times samplings are needed. So in aliasing, there are the frequency of input into two times is the frequency of analog sequence signal is two times of input signal. How ADC works, a glimpse under the hood. Different ADC architect balance speed, accuracy, and complexity. Here are three common approaches. First one is digital ramp ADC, a simple but slower method. It uses a counter and a DAC to count up until its output matches the analog input. Think of it as a climbing a staircase, testing each step until you find the right height. Simple circuit design, slower conversion time, good for low speed applications. The second one is successive approximation ADC, SAR, faster and more efficient. It uses a DAC and a comparator to guess the digital value, defining its guess bit by bit through successive approximation. The steps included moderate speed and accuracy, balanced performance, common in microcontrollers. The second step is clear, and the third method is flash ADC. The fastest step, it uses a bank of comparators to determine the digital value in a single step, but it requires many comparators for higher resolution. Extremely fast conversion, high power consumption, used in a single high-speed application. So the summary is analog to digital from smooth to step. This transformation captures the essence of ADC. A continuous following signal becomes a series of distinct discrete values. Each step represents a digital sample, and the precision of this step determines how faithfully we can reconstruct the origin analog signal. So conversion of analog to digital also we can call is encoding. So the reverse journey, we can see now the reverse journey, digital to analog conversion, DAC, analogy. Now imagine you have a collection of pebbles, digital data, and a need to create the smooth river. First one is digital input. Discrete numbers arrive from computer's memory or processing. Conversion. Each number is transformed into a corresponding voltage level. And third one is analog output. Continuous signals emerge ready to drive speakers or displays. Means in digital signal they have only discrete values, zeros and ones. They need to convert it into infinitely many infinite outputs. There is so here they have only non-continuous. We can see the non-continuous graph. So here they will convert the analog output into a continuous graph. A DAC takes a discrete digital number and converts it back into a continuous analog signals like voltage to drive a speaker or display. It essentially connects the dots between the digital values to reconstruct an analog waveform. The quality of this reconstruction depends on the update rate and the bit depth of the digital source. So why do we need both? Why do we need both? EDCs and DACs are everywhere in modern electronics. Service as the essential translators between our analog world and digital processing. So sensor and inputs, microphones, cameras, temperature sensors, touch screens, and pressure sensors all produce analog signals that need conversion to digital for processing and analysis. Second was modern electronics, smartphones and computers to medical equipment, automotive systems, and industrial control systems. ADCs and DACs are fundamental components enabling functionality. Third one is output devices. Speakers, displays, motors, and actuators receive digital commands but often need to output analog signals to function properly and create continuous effects. Critical applications: medical imaging, patient monitoring, industrial automation, telecommunication, and audio engineering all depends on precise analog digital translation for accurate result. There are many in this world. Our world is uh, depends on this bridge, the essential link, input and output. You can see that input port for ADC. This is converting the physical world. Like I'm speaking from here, physical world. It is an analog signal, and ADC converts means analog signal to digital conversion. It converts digital data processing so that you can hear that my voice. That is a digital to analog processing. In output, you can see that processing digital data, DAC analog signal, and physical reverse of ADC. In ADC, sensor captures analog signal. ADC converts to digital for computation and storage. In DAC, computed results converted back to analog to create real-world effects and interactions. This bidirectional translation enables the complete cycle of digital processing, captures, analyze, modify, and output. Without both ADC and DAC working together, digital systems would be isolated from the physical world. The impact shaping our digital world. Seamless interaction, silent heroes, and essential width. First, we see seamless interaction. ADCs and DACs enables the seamless interaction between the physical and digital world, making technology feel natural, intuitive. Silent heroes. They are the silent heroes behind the rich audio, vibrant visuals, and, and responsive interfaces we experience every day. Essential bridge. Without them, our digital device would be deaf, blind, and unable to interact with the real world. So, every time you speak to a voice assistant, capture a photograph, listen to music through headphones, or adjust the temperature on a smart thermostat, ADCs and DSs are working silently in the background. They have transformed how we interact with technology, enabling the rich multimedia experiences and intelligent system that defines modern life. From the smartphones in your pocket to the medical equipment saving lives in hospital, these converts are the invisible translators that make our digital world possible. So thank you for listening me. Okay, thank you.